third or first. All right, so our next speaker is Constantin Teleman. That's the line you're not supposed to. From University of California, Berkeley, and he'll speak about passée topology.
Yes, I'd like to thank the organizer for inviting me. It's a pleasure to be back in my old home in Edinburgh. The weather reminds me of summer in San Francisco. So, yes, I'd like to talk about how some, I think, very, very old style topology comes up, I think, to offer an answer to a question that's been bugging me and maybe several other people for some time, and that's part 6 of the talk, namely how to construct Coulomb branches for representations of G which don't polarize. So maybe the setup, so G is going to be a compact group, and usually I'll say connected and simply connected, or we can do away with that. Compact connected, simply connected in the group. And W is a symplectic representation. I should say not symplectic, probably is a bad word. Quaternionic, although it's SP that will show up in the notation. And it said both to be polarized if it's a double polarized. If W is B plus B check. So I should say that talk could take us 2 parts. Actually, the line kind of separates them a bit. One is somewhat old, and it's in the sense that it's already on the paper on the archive. That's a more interesting part, and it explains, I think, 2 things. First, that these Coulomb branches we've been hearing about, they're very interesting from the point of view of quantum field theory, but if you just want to think of them as algebraic varieties, and algebraic Poisson varieties, they're actually very easy to describe. So the first part is an easy description of the Coulomb branches in connection with, surprisingly, 2-dimensional gauge theory. So they're determined by that, very low dimension. And the new part, which is more or less below the line, is was inspired by discussions with Sam Raskin. First, I did not understand the content of the discussion much. I would just put my spin on it, which what I understood in the way that I would describe the Coulomb branches in the polarized case from boundary conditions, from topological boundary conditions of gauge theory. I think as a construction which proposes to describe the non-polarized case in terms of conformal boundary conditions. That's the part I would extract. But the important part I've learned from him, although I think in physics it was known for some time, is that there is an obstruction when W is not polarized to construct in the Coulomb branch, about to obstruction. So now that's the kind of thing I should be able to understand, I thought, and that's a new part of the talk, to locate that obstruction in some very old topology. So I gave this talk in Moscow some 2 weeks ago, and didn't quite get to part 6. So in order to avoid the same fate here, I'm going to give the talk in reverse order. Start at the end. I work back, no. I start at the end and then return to the beginning. So the end, because the end I can say some of it independently. Maybe. So what is Wood's theorem? It's about the interaction of real and complex topological K-theory. So Ku is a spectrum representing complex K-theory. So I'm trying to think of a space. I just write Z cross BU, but I won't do that again. Then, of course, some complex vector spaces are come as complexification of real vector spaces. So there is a map from KO to KU, the map of spectrum, potentially we'll see. So there is a cofiber of that map, and Wood's theorem tells you what the cofiber is and actually how to build the whole thing. The cofiber turns out to be a double suspension of KO, and it's classified by, of course, it's a map from sigma 2 KO to the classifying space of the sigma 1 of KO. And this this map is copying with eta, and that's unique class in KO minus 1 topology. Sigma 2 of KO is also known as omega 6 of BO, I think, and that is U mod SP, and that's also omega 2 of BSP. So we have a map of KSP and consistent. So I get the KU here and KO in the fiber. And this classifies something which could be called anti-symplectic representations. The representation which have J identifying them with a negative and J squares to minus 1. And then J. And the map from here to there takes a representation, I'm not calling it G, let's call it E, to E minus E check. And you can see at least why sort of dual representations disappear, but you can't see the signs. That's kind of a bad way to write it. Let's step back to meaning the loop twice, because of both periodicity I only need to write KU here. Here I will need to write sigma 2 of KO in the fiber. So the same sequence shifted in dimension. And now people might begin to understand what I'm talking about polarization, non-polarization. The map here takes a representation E, is double, is double. The complex vector space E2. So somehow a non-triviality of this, or a non-lifting here, is the obstruction to the existence of a polarization of a quaternionic space. And the map is omega 2. Where does it come up? Well, if you have a representation BG to BSP, of the quaternionic representation of Q, then you can form the index bundle over P1. And that's the G equivariant map from the modular of G bundles on P1, that's omega G mod G, if you don't this. Now maybe armed with the information I told you as an issue, problem another. One or two people in the room who know the construction of the BFN construction, the polarized case, might be able to come up with a guess how to do the non-polarized case. So this was Wood's theorem. This is how it apply to us. And we'll return to it at the very end of the talk if time permits. So, removing removing the obstruction. Right? Allows Coulomb branches are not polarized. Here I could have written G equals to B plus B check, because that matches what the representation. Oh, W is going to divide group 2. Never mind. And the obstruction, the only remaining obstruction when we do things correctly is going to end up to be a succession of mod 2 obstructions. So only some mod 2 obstructions. Remember, I think the last summer, I think, I talked to Dodi Moft in Oxford, we tried to come up with a guess of what the Coulomb branch was for SU2 and the standard representation. And we tried on different sides, and we always had to take a square root of a function, didn't have a square root. Just dropped it. I dropped it at the time until I learned about the obstruction. That was a bad example to try. For the standard representation of SU2, it's perfectly quaternionic, but there's a mod 2 obstruction. The smallest one you can take is a 4-dimensional representation. And then you can build. Okay, the end of section 6. Now let's start at the beginning. So, unfortunate enough that we had some really nice talks by Harold Williams and Baidu, so I really can skip most of part 0. I will just remind you that the Coulomb branch, what the Coulomb branch is from our point of view, there are 2 of them, is a space of functions associated to a 2-sphere in the 3-dimensional reduction of gauge theory. So, what should I say, Z of S2 in 3D reduction of gauge theory. And there are 2 3-dimensional reductions, as we heard, one along the circle, one along the line, and they give rise to a K-theoretic version and a homological version. So, reduction along R, you get the homology version, and along S1, we get the K-theory version. The connection between the 2 is reduced along S1, even if you ask for no energetic modes along S1, there is a topology along the fiber which shows up in an equivariant class, a degree 2 equivariant homology class. And if you invert that, you get a 2-periodic theory, which in examples we know ends up being K-theory. Some of the 2 are connected in the way that homology and K-theory are connected. And because it's a space associated with the 2-sphere, it doesn't need 3 structures. It doesn't need 3 algebra structure. And the structure could be called sphere topology. If you drop the dimension by 1 and instead of S2 you take S1, you get what's famously known as string topology. And the string topology operations are E2, and there's an entire story going with that. You can, in fact, construct cartoon pictures of such theories from purely topologically by sphere topology, and in fact the 0 Coulomb branch ends up being exactly that. It's naive. You could have guessed if you were thinking correctly somehow.
There's a spec missing somewhere.
Sorry?
So, functions on the Coulomb branch.
Functions on the Coulomb branch. Yes, C of the Coulomb branch, I should say. Yes, let's C of that. Regular functions. I don't know actually another way to define the space, but it's the fact. That also shows why, from this point of view, it's going to be difficult to say exactly what happens in one of the cases when I do a hyperkedar rotation, which makes it non-affine. So from my point of view, that's a very subtle thing, a hyperkedar structure. So everything I'll say will only refer to one particular complex structure. Syntactic structure going with that. All right, so let's recall the work on. That's part 1, the case of the 0 representation, and this is due to BFM, and for some reason all the contributors to this subject, well not all, a lot of contributors to this subject have in collaboration have very long names. I don't know what to do about that. So let me write them. Let me try to write the names down once. So Bezrukovnikov, Engelberg, Berkovich, one, then Braverman, different B, the same F, and Nakajima. And I think in the abelian case, which I think is relevant to number 4, some paper by Bullimore, Gayoto.
Well, I would say the abelian Coulomb branches were known for a long time in physics.
Before then, yeah. So I don't know what name I could put on that. If you want to suggest.
Abelianization maybe is what we did.
Okay. And what that one? Oh, GHV. Was that on the board maybe? GHV constructors. I gave it that away. that has to do with 2D mirror symmetry. Ivorian Baba are short names. I can never do that. More like that. Alright. So the construction was worked out. I mean, I think at the time they weren't thinking of 3 and 4D gauge theory, they think of Langland's duality, but it worked out very nicely, and they set up a lot of the properties that we still use today that are fundamental to understand the other Coulomb branches. So first of all, so there, as I said, there are 2 versions of the Coulomb branch, homological and K-theoretic. So one of them, so
Sorry, Constantin, I think it was you who at least recognized that the BFN.
that it was the BFN thing was the Coulomb branch. That's correct. But then they constructed the space and proved its key properties long before I looked at that. So first description of the space is spec of, or it's a ring of functions, spec of the equivariant homology of omega g with quadratic product. Second description is the other version is replaced with K theory as easy. So that gives you a ring of functions. Then so maybe that's the A is the ring of functions, and B, these are holomorphic symplectic algebraic symplectic manifolds. So algebraic symplectic manifolds. And they are resolutions of no case of the cotangent bundles of the maximal torus, complexified torus now I guess, mod the Weil group, or of the dual torus times the torus mod the Weil group. And the resolutions are explicitly given by a bit of blowing up, so I don't think I want to write formulas now, so explicit blowing up. I join some functions. I join some quotients, some ratios. The symplectic form, well, symplectic form has degree 2 and defines a Poisson structure and gives the 3 structure. So maybe I'll just say a bit about it. So symplectic form has degree 2 and defines the 3 structure. And in fact, you can get more than that. It's a leading term of a non-commutative deformation, which comes from making this circle equivariant. So, leading term of NC deformations obtained by rotation equivariance, loop rotation equivariance. We saw the picture, I think, in Duisburg yesterday. Right? Why is there a 3 structure here? Well, because you have some 2 spheres in space, and the multiplication, of course, can move around any way you like. That's usually 3. But if you insist that rotation equivariance be preserved, well, the only way to do it is to put them on a rotating axis, at which point you lose commutativity. An algebra, and the leading term of that is a Poisson structure. That's what I'm talking about. So this is what I mean by sphere topology. Actually, I should have made a remark. So the homology of maps, free maps from S2 to any manifold X has an E3 structure, and that's what we're talking about.
What stuff you from putting them inside one another?
No, it's a bit like it's a solid pair of pants, so to speak. It doesn't have a name. It's like this guy, but where instead of a circle you have a sphere, right? So I mean, oh, sorry, yes. If you have to put them in R3, that's right. I understand what you mean. Yes, you have a big ball, and inside you make 2 holes. So those are the inputs, and without the output. That's right. You can bet them in R3.
Composition is well defined. Bargisms, right? Still.
Yeah, it's this thing. One dimension. It's what it is.
S2 or doesn't matter what, right?
Sorry.
But
you could put other surfaces here, and there would be the structure of a partially defined TQFQ. You
This is beyond the BFM, right? This sphere, definitely, two spheres are beyond, right? This,
No, the two spheres they're hidden here because this really is one map at the sense of stacks from S2 to 2G. It's actually hidden there. And if you want to do it algebraically, you don't want to draw a sphere. I don't want to get. I have to say something about that when I get to part 5, so let me not get too much technical detail here. Right, so E. These have more structure than I just said. These are they're completely integrable systems, and they're known as, now we call them the total system, but in fact it's a slight improvement, which among literature has been dancing around for a long time without, sorry about raising the credits. I put them again at the end of the note. So, there are, oh, I see. Before that, I could do it. Before the integrable systems, that's right. No, actually, that's right, integrable systems. So they are completely integrable systems. Over, well, the Lie algebra modified group, or the torus spectrum modified group, which is of course spec of the equivariant cohomology of a point, or the equivariant case theory of a point. And that's a natural algebraic structure you get. And so F now. There are two realizations for the H version. I don't know the two realization for, I know only one realization for the K version. That is a problem for some purposes. One is symplectic reduction of the regular cotangent bundle of the dual group by the iso reduction. And the other one is a regular symplectic reduction of the same group but by n cross n of the opposing group at the regular opposing character. And of course they map compatibly to by the invariant polynomials of the fibers. And this guy contains at infinity the cotangent bundle of the dual torus, and this was traditionally called the total system. And now we understand it should be part of this bigger thing. Actually, even in the literature, people understood how to invent it, but somehow this nice theorem had been missed in the integrable system for a long, long time. And I
so it's not exactly by n and n, G on the left, n on the right. But anyway, it doesn't matter.
No, I think I wrote exactly what.
Different n.
No, it's the same n.
Different.
It's the same n, and it's and this is at infinity. You want me to write it that way? And it's the monoidal structures match. I guess it's important to use the same n. In fact, that's a good way to say it. And so let me tell you now the.
Sorry, can you say the K-theory case, which one you do and don't understand?
This one you can get from the loop group, although it might come with the wrong algebraic structure, but it does come with the right complex structure. If you try this, that's not quite right. You need to try something that find a difference to the system instead to make it match. But I didn't find it, I'm afraid. So the rings in question, let's say the ring in questions should act on the equivariant cohomology, or respectively the equivariant K theory with a 2 in front of every compact Hamiltonian synthetic manifold. And in a sense, they're universal, that property. I won't say exactly what, but they're universal operations like that. And that's a connection for two-dimensional gauge theory, and the story which connects them, I want to explain it now, is that, well, Coulomb theory or Fluor theory is a two-dimensional field theory. We have a group acting, it can be gauged, and that makes a boundary condition for three-dimensional gauge theory, and that's where this connection comes from in physics. But so let me tell you two things connected with that. Optimal method I have devised here. One we won't use, more difficult and interesting, but I won't use. The other one is easy and we will use. So, H. So in this space, this presentation has a preferred holomorphic Lagrangian foliation by the cotangent fibers. We can transport it here to a holomorphic Lagrangian foliation. So the vertical fibers we put R the reach mirrors of the flat varieties. Flat varieties. And R with small quantum parameters, I should say. And if you count the dimensions, you find exactly all the flat varieties and all the parameters that you need. Maybe I want to say GH with I. That's more difficult. The easier one is the one we'll use. You can write a mirror. You can see rather. GHV given the horizontal mirror of linear gauge theory. For M is V, a representation, complex representation of G with the syntactic structure coming from the unitary structure. And that I'll write explicitly. This one I will not write. But perhaps I want to say something about this action here and how it connects something geometric in the Witten theory from relevant to point I. So I think we said that these varieties are very close to valid quotients of the cotangent bundle of the torus. So let's actually lift the cotangent bundle of the torus. It will be a bit of a problem where the blowing up happens, but so let's ignore that problem. So we restrict from G to H. So you get the quantum cohomology of whatever M is as a module over the function of on the cotangent bundle of the torus. So it's of course a product of the torus. So it means we should get an action of functions on the Lie algebra and functions on the dual torus. Well, this part is easy because that spec of the equivariant cohomology of the point, so that acts on equivariant cohomology. So I have to tell you how these guys act. Well, functions, the Fourier modes on this are elements in phi 1 of HC. So C of function HC2 is a grouping of phi 1 HC. And elements of phi 1 act on what I call the Zeidel operations. So the content of the theorem is assembled together to an action of function the Coulomb branch, and this action has good properties, interchanging E3 on the Coulomb branch with the two structures secretly hides the quantum cohomology and so forth. There's a consistent story. In the torus case, you can define everything just by defining ingredients separately. So the non-obedient case doesn't break up quite like that, so it has slightly more information because of it. So a priori completely reducible.
Some naive question, sorry for interrupting you. It is about Dubrovin connection on quantum cohomology, right?
There is a relation to that, but I don't want to get into it. I think the structure of the Lie algebra has formal similarities to Dubrovin's connection, and the structure on this side.
Then you will immediately get operators like Todd operators. If you just say these words, right, more or less directly, you will get Todd, right?
You could do it that way. I think in that picture that's correct. Those difference operators are the shift operator. That is correct. That's the point here is that there's a Fourier transform-like relation in the two factors, because I didn't explain that, but this quantum cohomology would have Lagrangian support in here. So on one picture, the equivariant projections, the order transform the shift operator. That is a semi-classical relation for this step. That is the connection. Sorry, what was the question?
In point G, which version of quantum K-theory is that? I think there's different approaches.
Well, different approaches, but I think the K-theory, the modular of curves and integrating K-theory with covariant for the group, I think we can all agree what that is. I don't think I want to go into, let's say, Givendal's work on equivariant K-theory.
Should it also act on Okunkov's quantum K-theory of cyclic resolutions in terms of quasi-maps?
Doesn't he have the equivariant setting where the circle scales symplectic form? It's not the Hamiltonian setting. So we're not in that setting.
He usually also has an equivariant.
Oh, the equivariant. Are you asking how to compute things?
Well, I'm just asking, is that quantum K-theory, will it also act on that notion of quantum K-theory in terms of defined by quasi-map spaces?
So, as far as I know, it's not universally true, and they agree. Okay. It's not universally true almost that even the cohomological versions agree in the final case with a dimension computation. But in K-theory, you can't use that. So you really have to use the honest thing. You have to use just stable maps and the G action on those. Okay. But so what did really? Okay. Alright, so I think the next thing I'll tell you the linear case, and then we'll be able to characterize the Coulomb branch in terms of gauge field representation instead of this construction, and then I'll try to go quickly to 4 and 5 and say a word about 6. Okay, so now we have a representation, a complex representation of G, so dG to GL of V, so dGL of V. And as before, you can form over, you have the universal bundle, G bundle, DC bundle, over P1, that's over P1 across, of course, band G of P1. So you can take the associate bundle, so use B for associated bundle. And take now, so this projects to E1 by pi, you can algebraic geometry, find our star of V, tensor square root of K, should we do that? That's the bundle gives you a map from topologically, just from band G of P1 to omega, well, to omega u, the g actions, or maybe I'll write the honest thing from omega g to omega u, and it's equivariant for g. Yeah, it's here. There's a compatible reaction there. This u contains representations of g. That's the index bundle. And the index bundle has a nice property that's additive. Additive for the convolution product or contrarian product. That's because, you know, here's a picture of a bundle here, a bundle there. The index over the union is essentially the sum. You can see by deforming a bit to a single pure. It's in fact E2 additive, and it's E3 if you take the equivariance, but that's nice to know. But so if you apply a multiplicative characteristic class, from Ku added with addition to K, say K theory with multiplication, you get a multiplicative class. You get a multiplicative class, multiplicative element in the equivariant K theory now of omega G, and it's a Hopf algebra dual to the Coulomb branch. Generated by the group multiplication. So if a multiplicative element in the dual Hopf algebra tells you have an element of the group, in other words, a section of the Toda system. So maybe I want to write something. Let's write the obedient case and have H check in the fiber H or H in the base, if you like, to divide by the value. So it tells you that somehow there's a unit section, and somehow it's going to be a section defined when you choose a multiplicative characteristic class here. Just from the representation of B, and there's a nice one, which is the Euler class. It's a nice example. It's almost nice. It's almost nice because an unstable class. K theory. If you're in K theory, you have to take the theory. It's an unstable class, and this is a virtual bundle, so actually it has denominator. It's rational. It's not integral. You can improve it slightly, and you need to. The total Chern class. The parameter, homogenizing parameter mu. Mu. So it's really something like summation of mu to the minus n c n of the index bundle. Let's call that epsilon b of mu. By the way, the total Chern class is the Euler class made equivariant for the overall scaling action. You still have singularities actually. A priori actually is just the Laurent series negative powers of mu, it ends up being rational. That's rational. Parameters of H. But it still has poles. It's just you have an extra parameter to play with to desingularize when you want. And this is called one of the flavor parameters in physics. Alright, so here's a proposition. First of all, obviously you should be able to compute that, because after all, you can compute it by reduction to maximal torus and then just do a computation. You can compute. I can give you a formula, but I'll tell you the interesting thing about it. Well, the first claim, I didn't say it, but it's does it follow from what's on the board? Probably not. So fact 2. Lagrangian. That's tied to the fact that it was transgressed from here. It's a bit like a derivative. So it's actually the graph of a differential of a function. And the function is something like, if I remember, mu and an element sine h goes to something trace in v of let's say x times log, so let's call this guy x, log x minus 1. And people who know mirror symmetry will recognize the formula that comes from mirror symmetry, and the statement is the Legendre transform of this the given Tal-Hori-Vafa mirror for the representation of mirror. Pull back the maximal torus in this case. So the Legendre transform is the GH mirror of V with a covariant scaling by mu, so maybe scaling by mu. Pull back. So that's a calculation, but somehow it looks like a miraculous accident. It isn't. Let me try to just, last thing I'll say about quantum common, try to explain why that comes about. Okay, maybe I won't explain why it comes about. We can't take both sides after all. But let me explain what it does. Let's write an example first of all, the simplest one. Simplest one would be GL1, U1 acting on the standard representation. So example, U1 acting on standard rep. Okay. Then in degree, so what's omega g? Just the integer as equivariant for U1. So ban g is just b1 plus z. So U1 will act on the index bounded by the standard vertical type on L. So at a point n in z, the index, or what is it? Well, h1, h0 is n-dimensional, and h1, sorry, n greater than equal than 0, and h1 is 0, and it flips when it is negative. N. So the Euler class is, I think, what they call the parameter psi to the n over n. Psi to the n as an element in the equivariant homology of a form. And if you add a scaling parameter, you get the scale. And if you think through what that means, it tells you that the Lagrangian we're talking about, so coordinate here was psi, let's go give it a name, maybe z. Lagrangian is z equals. It has a pole actually. It has a 0 when psi is minus mu, but the 0 is just as bad as a pole because you want to land in a group. So pole at psi is negative. So what happened before? So before I said for a compact symplectic manifold, you'll be able to act with function of the Coulomb branch. This is the Coulomb branch for functions on this side, Coulomb branch of U1, on the quantum cohomology of a compact symplectic manifold. So now I took a manifold, which is a line L, and is not compact, And indeed, when you try to act on the quantum cohomology, you'll find there's a little glitch. It doesn't quite act. And it doesn't quite act, the explanation is geometric, is because what you'll be trying to do, how do you get a function h, an element of phi 1 to act? You construct a bundle of a P1 associated with that element of phi 1, so gamma of phi 1 of h. Construct a G bundles and they use a 2-point function, so pull back from cohomology of n to cohomology of n. In this case here is map sections over P1 of the M bundle. So we want to pull back, push down. That's how we define the operation of quantum cohomology. And the trouble is if you have a vector space, well, if you don't have any bundle, you're perfectly fine because all holomorphic set functions of vector space are constant. But if you twist the bundle, you begin to have sections. When you have sections, this math is no longer proper. Integrating over something non-compact is what's causing the split. So the non-compact version, the best expectation is that the Coulomb branch, so H star G of omega G, acts on the symplectic cohomology, of N, for non-compact G. And that's exactly what happened. If you go and compute the symplectic cohomology of a vector space, it can be done. You find it completely consistent with this. That's exactly what happened. Alright, so now let's do 3 very quickly. And then we'll do 1 minute, I'll do 4, 5, and 6. Yes. 3 characterization. C of G, B plus B check. And these are several equivalent conditions. The meaningful one kind of already appeared here, but it becomes very concrete very quickly. So let me start with the abstract one just to tie it in. So functions of the Coulomb branch act on the equivariant quantum cohomology of n manifold upon n cross q, where n is compact. And you want the scaling on B, so maybe G cross scaling. That's a new parameter. And it's a universal thing which acts in the same determining of this size, which has to conclude. So this guy is a subring of functions on the Coulomb branch of 0 representation. And it's characterized as a subring of those functions which survive translation by which means that you want the conditions that f is a regular function, and f composed of multiplication by epsilon, vertical multiplication is regular quantity. And if you think a bit what this tells you, well, this, as I said, this thing will have some poles somewhere, so it goes to 0 infinity on the torus. And at those poles, you need a vanishing condition on f, so that it survives that translation, and you can spell out what those conditions are. You can impose those conditions, if you like, by some, putting the condition at infinity. You could also compactify, blow up, and then remove the boundary. So the geometry and combinatorics that governs these things is in fact very similar to toric geometry. Just toric geometry over the base, and the group, instead of being just the torus, is the total system. The historic geometry. Control combinatorial. Geometry. I'm confident a huge amount of combinatorics can extract from it, but I'm skeptical as very new. I mean, it's a variant of toric geometry. It's not exactly that, because in the non-obedient case, after all, the groups can degenerate a bit, but it's controlled by the same sort of combinatorics. I'll just give a very quick example, so it's not all theory. SL2. So quickly into 5 and 6. SL2. Take a representation W, which for now could be B plus B check, but actually it won't have to be. From that you can extract a number N, which is 1/2 of the sum of positive weights. So that number had better be an integer, and that's a multiple abstraction. And then the functions, well, let's recall the function of a Coulomb branch of SU2 the zero representation first. This is from the original BFM theorem. These are, when you start with z plus minus psi, and then you adjoin z minus 1 over psi, and taking variance of the divided group, which is plus minus 1. So psi goes to minus psi, and z goes to the inverse. And if you want to say what it is, it's going to be a ring generated by psi squared z minus z inverse over psi z plus z inverse minus 2 over psi squared, and I think we're done. And now with W, you're going to have, let's assume n is greater than 1. N is 1 in a single example of the standard rep plus the standard rep. If n is greater than 1, you get C of psi squared, psi to the n minus 1 times z minus minus 1 to the n z inverse, and psi to the n minus 2 of z plus z inverse and z plus minus 1 to the n z inverse, and don't need to subtract the 2 anymore. Actually, if n is not greater than 1, I could write it this way, and then it's completely correct all the time. But once n is 2, it's kind of obvious. You can compute it from that description. Why is the SU2 computation enough in a sense? It's because the ring of functions is free over a total base, so any funny thing to determine is in co-dimension.
Practically, I understand you could not have. But you need V plus V prime for symplectic structure, or just to ensure that it is even
if
number.
there is no V plus V prime, there is no V, and then the previous
just
story
even
makes no
numbers,
sense.
not
But
even
for
numbers
this,
only, right?
well, I haven't defined the Coulomb branch, but it's actually true. What I said is true. This is the Coulomb branch for the non-polarized case as well. The point is number 4. It's pretty obvious from the from one of the descriptions, the one that, for example, that Harold mentioned yesterday, that away from the root hyperplanes, you can reduce the maximal torus in the Weil group. So only the obedient branches need to be computed, as Tudor said they have. So if you can compute SL2, you can compute generally the root hyperplanes, you know, because it's free over the base. In the sense that that's it for the cohomology version. Of course, this was known BFN. They didn't write it this way, so also know BFN already. Polarized case.
So you mean Z plus Z
I forget the inverse.
Second argument is
Z minus the
plus.
inverse. Z plus the inverse
Minus
minus 2.
plus.
This is a plus.
And the second argument.
Z minus the inverse. I think it's correct. Is there something?
The denominator.
No, it's right.
Oh, it's
also
also
two
two
sides.
sides.
Sinus minus the order of vanishing at 1 tells you what you're allowed to put here, right? I mean, that's where it comes. It vanishes to order 2 at 1. So it's the way to explain that, but not in -1 minute. So let me just state the good hybridization theorem. I like to call it the Weierstrass formula for Coulomb relations. The special case already appeared in DFN. So let me write it this way. The Coulomb branch of G with the representation W is isomorphic the Coulomb branch for the maximal torus. W minus the double of G mod H. I put in quotation mark because it needs explaining. Oops. False, of course. Mod the Weil group. That's really bad. Let's check this. Okay, so the explanation, let me say it this way. If G is a sub-representation of E, then it appears twice actually by some symplectic condition, then this is true in stable homotopy. It's a stable splitting of the BFN space. If G is a sub-representation of E as an H representation, the roots of G appears among the weights of G are among the weights. This is true in K theory and cohomology. And then the right hand side is completely meaningful. You can subtract the representation from the restriction of equal. In cohomology, it's an even stronger result, which you can see from here. If n is large enough, some number computed on the weights is large enough, there is a statement like this, but here I have to put another representation with matching numbers. So in cohomology, version for all but finally many. So that tells you even how to compute, I think, the non-polarized Coulomb branches. Now I'm out of time, so I think I will not return to 5 and 6.
Further questions?
So was this intended as a definition in the non-polarized case?
The theorem. The definition I almost told you at the beginning, but the non-polarized case, if you 10-second answer, there is no space that's analogous to the BFN space that's obstructed by the extension I wrote to you, but that extension is by BO. So now, if you can get rid of it somehow by applying a suitable cohomology theory, you can build it. So with BO you can't do very much, but if you can lift it to BSO, there's a mod 2 obstruction for that, that's n mod 2 actually, that's n over 2 mod 1. Then you can apply cohomology to that, because the Thom class in cohomology kills the orthogonal group action, so that extension disappears, and you have a spectrum over cohomology. If you can lift one more obstruction, you can lift it to spin, you can smash with K theory and get a K theory spectrum. So there is no space you could use to apply cohomology to it to get the Coulomb branch. But if you apply cohomology first, then it exists. That's it.
Does the answer still have the same form via a Lagrangian section?
I don't know a description analogous to the simple description I gave in the polarized case because I don't know enough topological boundaries. That I don't know. So that's the only computation I know. It's very awkward, but it's the only computation I know how to propose.
Constantin, but your formula makes perfect sense for half integers, of course, right? So we just don't have geometric interpretation, right? Okay, it's half an integer, so what is better about the answer, right?
Well, z to the 1/2 is not in the not a subring of this guy. So it's a double cover somehow. You could define the space, be able to define. I didn't tell you some of the properties, but all the other Coulomb branches are torsors over the 0 Coulomb branch. So this would not be like that. If you take a square root, it's something that wants to be a double cover of a torsor. Yes, but yes, that's a kind of obstruction.
So you mentioned Hori-Waffa. So Hori-Waffa is construction for the quantum homology of toric variety. What it appears.
Well, if you take G and reduce it to a torus, it's a toric variety. So it's a representation. Toric variety, and it determines the other stuff.
So you're saying that the Williamization, for generalization, you can use Hori-Waffa and it recovers everything else?
I'm saying that if you write what you get from Hori-Waffa, you write the correct Lagrangian for the non-obedient case, and that is the one that goes into zero. This Lagrangian has been defined independently as the order class of the index number, right? Without the quantum homology. And I'm telling you, when you write out the formula, you find what Hori-Waffa would have told you if you're reducing the torus from the bias group.
Okay. So basically,
It's alternative computation.
Some enhancement of Hori-Waffa works. So when you have this one
You could say the entire story of the connection, the quantum homology, and the Coulomb branch is an enhancement of Hori-Waffa. I would like to say that.
It's the same as given type formula for torus, for toric variety.
That's why I put given type in there.
Wow.
There are many given type formulas, but yes, and there's a naive combinatorial formula for the quantum equivalent quantum homology of what the mirror of a toric variety should be, and this generalizes that.
Other questions? All right, let's thank Constantin again.